Hello everyone, welcome back to another session for thermodynamics subject. In previous session or previous sessions actually, we have started to discuss about second law of thermodynamics. I introduced you the uh, irreversible and reversible cycles and processes as well. And I told you that to have the most efficient heat engine, we need to have a reversible heat engine, which the most common type of this reversible cycle actually is Carnot cycle. And as I told you, the maximum possible efficiency for a heat engine or these cyclic devices is when we have a Carnot cycle. Then to determine this the efficiency or thermal efficiency or coefficient of performance for this kind of devices, these cyclic devices, we need to use that equation if you remember for the thermal efficiency. And that coefficient, if you remember, was we had the equation like this. Generally, which QH is the heat, which is amount of the heat which is rejected to the uh, uh, heat source with the or heat reservoir with higher temperature, and QH is the amount of the or which is captured actually. This QH and QL is the amount of thermal energy which is released to the sink. And if you notice here, to find thermal efficiency for this kind of devices, we need to have QH, QL, or we need to have W divided by QH for these devices and so on. And in all of these equations, as you can see here, we need to have QH, QL, and so on. Such different properties or different variables which we cannot measure them directly, and it is not that much easy to measure them to calculate the thermal efficiency of a cycle, especially for a Carnot cycle. Then if we have properties, and as you know, we may guess this QH or QL amount of thermal energy or energy which is released or rejected in a cycle. We may guess that there is a relationship between temperature of that reservoirs, those two reservoirs may be related to the temperature of those uh, reservoirs. But as you know, this QH and QL, however, may be dependent on the temperature of the reservoirs. If you remember, we had two reservoirs. This one has a heat source, which uh, QH, we give QH to this one, and its temperature actually is TH, and the sink, which we give that QL, and its temperature is TL. Heat engine, then give temperature to this one, and or capture and from this produce work and release QL to the sink. If you remember this equation, this schematic actually. Now, as you can see here, we may guess there is a relationship between QH and TH or temperature of the reservoir. But for different reservoirs, because we may have different substances, this QH is also dependent on the other properties of the substances, not only temperature. So we need to find a scale of temperature, which by using that scale, we can ignore other properties of the substance, like the type of the working fluid, for example, which which will determine the QH or QL. So this scale for the temperature is called thermodynamic temperature scale, which is independent of properties of the substance. And you may already know about that. If I introduce, you may recall that this scale is actually called Kelvin, and we show that by capital K. And this temperature, as I said, it will offer great conveniences in the thermodynamics to calculate, especially the efficiency of reversible heat engines. Here we have the proof and the procedure to find this scale actually. Let's start with a imaginary device or imaginary arrangement of three different reversible heat engines like what you can see here. We have two reservoirs, one of them with T1, the other one as a heat sink with T3, which the temperature of T1 is higher than T3. As you know, the heat engine will capture energy or thermal energy from the heat source. It will produce work and release a fraction of that thermal energy to the sink. Imagine we have these two reversible heat engine A and heat engine B. Heat engine A capture directly from the heat source, capture thermal energy equal to Q1 from the thermal energy reservoir and produce WA amount of the work and we release Q2, which is the amount of energy which is going to be released to the reservoir with lower temperature. But here we put another heat engine, which this QL for heat engine A is the input or thermal energy input for the heat engine, uh, uh, the B heat engine actually. And the heat engine B also will produce WB amount of the work and will release Q3 amount of thermal energy to the heat sink, which its temperature is T3. And also, in the other hand, we have heat engine C, which directly capture Q1 from the reservoir with higher temperature or heat source and release Q3 amount of energy directly to the uh, reservoir with lower temperature of T3, and it produce WC amount of work. This heat engine produce WC amount of the work. And as you notice here, we have an arrangement like what you can see here. We have one heat engine here and two heat engine here. These will help us because according to the first law of thermodynamics or conservation of energy during this process with two heat engines, we can there isn't any possibility for any heat uh, destroy or any heat generation during this uh, mm, work generation by these two heat engines. So Q1 and Q3 actually should be equal. Then the work which is produced, WA, WB, by these two heat pump will be equal to WC. Now let's see how we can calculate the thermal efficiency for each one of these pumps and how we can determine that the efficiency of, and if we can find efficiency equation to find efficiency of for this reversible heat engine. This is also important. All of these three heat engines are reversible or Carnot cycle actually, or Carnot heat engine. To find thermal efficiency of this engine, as you know, we can use this equation. Thermal efficiency is equal to 1 minus QL divided by QH. Then you can see here that thermal efficiency is a function of the thermal efficiency is a function of the temperature of reservoir of those two reservoirs actually. And also you know that QH and QL are a function of the temperature of those temperature of those two reservoirs. We can write this equation that QH divided by QL is a function of TH and TL as the temperature of uh, these two reservoirs. So for heat engine number one, we QH is Q1, QL is Q2, TH is T1, and TL is T2, as it is mentioned. And for heat engine, uh, the B heat engine actually, Q2 to Q3 is a function of the temperature of the T2 and T3 as it is mentioned. This is just substitution of these the values for these parameters in these two equations. And for heat engine C, we can write like this: QH is Q1, QL is Q3, and which is a function of T1 and T3. We have these three equations which shows the uh, relationship between the thermal energy of those two reservoirs and their temperature for these heat engines. If you look at this equation, we can write this Q1 by Q3. Simply we can multiply the numerator and denominator by Q2. Then Q1, if I want to write like this is Q1, Q3. If I multiply by Q2, we can have this Q1 multiplied by Q2, Q2 multiplied by Q3. And again, we can cancel them and we can have Q1, Q3. So we can write like this. And if you notice, Q1 by Q2 is F is a function of T1 and T2. So Q1 by Q3 is F T1 and T3 right here. Q1 by Q2 is F T1, T2. Q2 by Q3 is this function of T2 and 3. So we can write this equation like this. Then to find a relationship between the temperature of the reservoirs and this function actually, or we can write like this, which we have this equation for T1 and T2. This is an arbitrary function actually, which shows the relationship between the temperature. This is a function which we have actually between the temperature of T1 and T2. So we can write F T1 and T2 as phi T1 by phi T2, and for T2 and T3 also we can write this function. Phi is the arbitrary function which shows the relationship between T2 and T3 actually, or T1 and T2, the temperature of both of those two reservoirs. We imagine that here this function is like this. This is just an arbitrary function actually. And then this ft1 and t2, or this ft2 and t3, if we substitute this phi t1, phi t2, and phi t2, phi t3 in this equation, and if we cancel this, we will have this. You can see here that we have equality actually between the thermal energy of first reservoir, or actually we have a equality between the ratio of the thermal energy of the first reservoirs and the second reservoir and a function of temperature of the first reservoir and the second reservoir actually. So we can have this equation. And if you remember, we had that general equation and we reach here by using that general equation. Then we can write QH divided by QL. Q1 is QH, Q3 is QL, and these T1 and T3 actually are TH and TL. We use this illustration to write this equation actually. So this equation shows that this ratio, the ratio of QH to QL, is equal to TH divided by TL. But we cannot write directly TH and TL because TH and TL are in a function which is an arbitrary function. So we can have this equality, but we need to find this function. The most simple type of the function which we can write is to assume that this th or this phi th or phi tl is equal to a t, or phi t equal to t. This is the most simple function which is proposed by Lord Kelvin, and we can rewrite this equation QH by QL for a reversible cycle is proposed by Lord Kelvin, that this ratio is equal to this ratio, temperature of the reservoir with higher temperature divided by temperature of the reservoir with lower temperature. So we have this equation. But here T and TH and TL need to be defined by a new scale actually. This new scale is called Kelvin scale, and temperature on this scale is called absolute temperature. And this is according to, and our purpose actually is to reach this statement. For a reversible cycle, the heat transfer ratio, QH by QL, can be replaced by the absolute temperature ratio, or TH by TL. But what is this absolute temperature actually? The absolute temperature, uh, the uh, the absolute temperature, we need to define that. Moreover, we need to know how much is the magnitude of this absolute temperature. However, you may already know about that. I explained here, and you can see here why we have this scale for temperature. That equation which we have, which shows the relation, the two ratios, one of them is for the thermal energy, the other one is for temperature, gives a ratio only, and we need to know how much is the magnitude of this Kelvin scale for temperature. In a conference in 1954, the triple point of water, which you already know about that, it is the state at which all three phases of water exist in equilibrium. We have we have liquid, we have solid, we have vapor, or we have steam, we have ice, and we have water. All of them together in an equilibrium state. Actually. Then this amount of temperature was measured, and it was assigned with the value of 273.16 K. So we select that temperature, we measure that and select that as this temperature. That equilibrium temperature of the water at equilibrium state, we measured that and we selected that as the 273.16 Kelvin. So the magnitude of a Kelvin is defined as 1 divided by the amount of the temperature. So the magnitude of a Kelvin is defined as 1 divided by 273.16 of the temperature interval between absolute zero and the triple point of a water. So you can see here how this Kelvin temperature is developed actually, and the magnitude of temperature unit in Kelvin scale actually is equal to the magnitude of the temperature in Celsius uh, scale actually. 1 Kelvin of temperature is 1 degree Celsius temperature, and to convert Kelvin or Celsius to each other, we can use this equation, which you may already know about that. Temperature in a Celsius scale is equal to temperature at Kelvin scale minus 273.50. Or vice versa, to find Kelvin, we simply can add this number to the temperature in Celsius. And this this Kelvin temperature actually help us to find the efficiency of different type of engine or heat engine actually, and it help us to find the efficiency of Carnot heat engine. As I said earlier, the efficiency of the heat engine, which works on a Carnot cycle, is called Carnot heat engine, which I have already discussed about that. And as I said, according to this equation, we can have this equation to find thermal efficiency of a Carnot heat engine, which thermal efficiency of a Carnot heat engine, which is a reversible heat engine, actually is equal to 1 minus TLTH, because as you know, we have this equation for any type of heat engine, irreversible and also reversible heat engine. If we have QL and QH, we can find its efficiency, its thermal efficiency by this equation. We have seen this in previous slide. So thermal efficiency is equal to 1 minus QL divided by QH. And as I showed to you, we have this equation, and QHQL is equal to THTL for a reversible heat engine. So we can substitute TL and TH in this equation to find thermal efficiency of a Carnot cycle, which is the maximum possible thermal efficiency for a heat engine. The most important thing for this equation is TL and TH should be substituted here in terms of a Kelvin scale for temperature. So TL and TH are absolute temperature are Kelvin to find the thermal efficiency of a reversible or a Carnot heat engine. And generally, we cannot have a heat engine with higher thermal efficiency than the thermal efficiency which we have for a Carnot heat engine, which that Carnot cycle works between the same temperature of that the other heat engine which we have. So for example, for a heat engine, like what you can for we have three different heat engines here. They are working between two reservoirs with same temperature. If you notice, the the heat source and sink for all of the heat engines are same in their temperature is same for each one of these heat engines. Then if the temperature, if the thermal efficiency of the reversible heat engine is 70%, for a reversible heat engine, thermal efficiency should be lower than 70%. And we cannot have any heat engine with a thermal efficiency higher than this thermal efficiency, which is for a reversible or a Carnot heat engine actually. And this is shown also here in this statement. So the maximum possible uh, thermal efficiency for a cycle is for Carnot cycle. This is very important because, however, the Carnot cycle or Carnot heat engine is not an actual heat engine, and we cannot have a Carnot heat engine in real world due to because we imagine the Carnot cycle. In Carnot cycle, we have all of the processes in Carnot cycle are reversible. And we imagine that the Carnot cycle is 100% reversible cycle. But in real world, actually, we cannot eliminate all of the sources for irreversibility. So for sure, in actual, we cannot have a Carnot cycle or Carnot heat engine. We may have even a small value, but we have irreversible. So why this Carnot heat engine or is important, and why thermal efficiency of this Carnot heat engine is important? Because we can uh, evaluate the heat engine which we have. We can check for our heat engine how much can be the theoretically, how much can be the maximum possible thermal efficiency. Then we can compare our engine thermal efficiency which we have in actual, compare that with the Carnot heat engine, the thermal efficiency of Carnot heat engine with same characteristic. I mean the which works between the same temperature, uh, high and low temperature actually. So to check the heat engine, we need to compare thermal efficiency of that heat engine with the thermal efficiency of the Carnot heat engine, which works in between the same temperatures actually. And so however, the efficiency of actual uh, heat engine may just be 20 or less than 40%. But if we compare that with the Carnot cycle, we may find out the thermal efficiency of the our engine, which we have in actual, is 70% of the thermal efficiency which we have for Carnot cycle, for Carnot heat engine. So we can see how we can use this Carnot heat engine to check the performance or efficiency of our heat engine. Moreover, we can also understand from these equations how we can increase the efficiency of the heat engine, actual or Carnot heat engine. To, as you can see here, to increase thermal efficiency of the Carnot cycle, we, uh, we need to reduce this. To reduce this, we need to increase temperature of the heat source or the reservoir with higher temperature, or reduce the temperature, reduce this TL, or increase TH. Reduce the temperature of the heat, heat source, or reduce temperature of the heat sink. And this is the method which is usually being used to increase the efficiency of the different type of the heat engine. However, we have limitation to increase this TH, which is because, as you know, the heat source may be a boiler, then the strength of the material against the high temperature will determine the maximum temperature which we can have for the reservoir with high temperature or heat source. And TL is temperature of the sink, which is usually a condenser or a lake or ocean or something like that, which is temperature we can be a certain amount of temperature, and we cannot reduce that as much as we want. So we have a limitation also for manipulation of the temperature of those reservoirs to increase the efficiency of these heat engines. Here we have two examples to see how we can calculate the thermal efficiency for these Carnot heat engines, and also other type of or irreversible heat engines actually. Here we have a Carnot heat engine, as you can see in this figure. It receives 500 kilojoule of heat per cycle from a high temperature source, which its temperature is 652 degrees Celsius. As you can see here, TH is 652 degrees Celsius and QH is 500 kilojoule. And this Carnot heat engine rejects heat to a low temperature sink, which its temperature is 30 degrees Celsius. TL is equal to 30 degrees Celsius. Now we are interested to determine the thermal efficiency of this Carnot engine or eta TH, and also the amount of heat which is rejected to the sink per cycle or QL. So we are going to find eta TH and QL. Simply to find the answer for this question, we can write this because it is mentioned we have a Carnot heat engine, so we can use this equation. Thermal efficiency of a reversible Carnot heat engine is equal to 1 minus TL divided by TH, which TL is the temperature of the sink and TH is temperature of the heat source. We have both of them, but in terms of Celsius, in Celsius scale. So the note here, what you should notice here is to change the unit of the temperature from Celsius to Kelvin. So temperature of TL is 30 degrees Celsius plus 273 will convert the temperature from Celsius to Kelvin. Same for TH, which is 652 plus we need to add 273 to that, and it is converted to the Kelvin. So the thermal efficiency for this Carnot heat engine is 0.672 or 67.2%, which is a significant or a high amount of efficiency for a heat engine actually. And to find the answer for part B, as you remember, we had this equation QH to QL was equal to TH to TL for a reversible cycle. So if we rearrange this equation to find QL, actually we can just change their position and restructure this equation and write according to the QL, which QL for a reversible heat engine is equal to TL divided by TH times QH for a reversible heat engine. We have TL, we have TH. Just notice we need to put in the equation in terms of Kelvin scale for temperature, convert to Kelvin scale, and we have QH as well, which was mentioned is 500 kilojoule. And please notice here QH and QL are positive, as I said earlier, because we have already assumed direction for them. So the value for them are positive. This is the important thing you need to notice to calculate these values. So QL is 164 kilojoule per cycle. 500 kilojoule is captured by heat engine from the heat source, and the 164 kilojoule is released to the sink. So the difference between them is W net out of this Carnot heat engine actually. As I told you, we can increase the efficiency of Carnot cycle or any other type of the Carnot engine, Carnot heat engine, or any other actual type of heat engine by increase the temperature of the high temperature reservoir or reducing the temperature of the low temperature reservoir. So as you can see here, the temperature of the reservoir is effective on the uh, thermal efficiency of the heat engine. As you can see here, by this equation, as I told you, we can calculate the thermal efficiency of the Carnot heat engine, and as I told you, increase reduction of this or increase of this will increase the thermal efficiency. And this is what you can see here. If we have a constant temperature for TL, or the temperature for low temperature reservoir, and we change the temperature of the high temperature reservoir, the thermal efficiency will change like this. As much as the temperature is increased for TH, the thermal efficiency is also increased, and you can see the range. When temperature is 350 Kelvin, efficiency is only 13.4%. And when temperature is increased to 925, the thermal efficiency is increased to 67%. Almost it is 50% increased the thermal efficiency for this heat engine. And this is more important. If you notice here, QH can be constant for all of these uh, uh, heat engine action. So the amount of energy or quantity of the energy which is captured or released may be same, but the temperature of the reservoir or temperature of the each one of the reservoirs is effective on the thermal efficiency. So by increasing the temperature, the thermal energy of the thermal energy also will increase. This is called as the quality of the energy. So the quality of energy when temperature uh, is higher than the quality of the energy when temperature is lower. In other words, up to now, according to the first law of thermodynamics, you know that if we have 100 kilojoule of energy, we may convert it uh, to the work or a fraction of that. For example, if efficiency is 70%, it means 70% or 70 kilojoule if we of that energy can be converted to the work. In other words, if QH is 100 kilojoule, we if the efficiency is the 70% means we can convert 70 kilojoule of that to work, and QL will be 30 kilojoule. But according to this, when the temperature of the high temperature reservoir actually is higher, this efficiency is higher. It means more fraction of the uh, input or provided energy can be converted to the work. This is the quality of the energy actually. If the temperature of the this reservoir is lower, the work which we can get from the same amount of the energy will be lower. For example, if QH is again 100 kilojoule, but the temperature is lower, then the thermal efficiency is only, for example, 13%. Then it means from this 100 kilojoule, only 30.9 kilojoule work can be produced. And rest of that QL will be rest of this value actually, which is almost 64 kilojoule will release to the thing. So you can see here, not only the quantity of energy is important, but also the uh, quality of the energy is important. The energy with higher temperature has a higher quality to be and more appropriate to be converted to the work. This is the reason actually if you notice, for a solar collector, for the to use the solar thermal energy, we usually use those concentrators to concentrate the sunlight and increase the temperature of a liquid or something, to increase the temperature which we can get from the sun. We, by those devices, we increase the quality of the energy actually. To make it more clear, we have a simple example here actually to show what I mean from the energy, the quantity and quality of energy. Here we have a simple example. We have two-person here. Andy has 10 friends, and Wendy has five friends actually. But those 10 friends of the Andy are only available for party and in the good times actually. But those five friends of Wendy are available even when the Wendy is in the problem, or if Wendy need them. So which one of them are actually the quality of which the friends of which one is higher? In other words, the quality of the friends of Wendy is higher than the quality of the friend which Andy or has. So it means these five friends are available, can help the Wendy, but those 10 friends are useless actually. This is same for the energy. However, we are interested generally to judge the energy in terms of quantity, because it is easy to measure the quantity of energy. But we need to also check the quality of the energy to understand if that source of energy is appropriate to be used, to be converted to work, or to be used as a source of energy for heat engine or different type of the devices which convert the thermal energy or other type of energy to each to the work and so on. Here we can also continue our discussion about Carnot heat engine and extrapolate the definitions of the Carnot heat engine to the Carnot refrigerator or Carnot heat pump. As I said earlier, the Carnot cycle or reverse Carnot cycle is called uh, uh, the Carnot refrigerate cycle actually, and by it means that this cycle or Carnot refrigerator cycle or Carnot refrigerator heat pump will produce highest or the maximum coefficient of performance for refrigerator or heat pump. And we cannot have, similar to the heat engine, we cannot have any refrigerator or heat pump we, uh, which can have higher uh, coefficient of performance or COP than the COP which we have for the Carnot refrigerator or Carnot heat pump. If you remember, we had this equation to calculate COP or coefficient of performance for refrigerator, and this equation to calculate the coefficient of performance or COP for heat pump, which QH and QL are the amount of the heat release to the heat source, QH, or heat release during the cycle, during each cycle to the heat sink. And we had this equation for any refrigerator or heat pump. But for Carnot refrigerator or Carnot heat pump, we can, similar to the heat engine, we can substitute QL and QH by TL and TH, which TL and TH are temperature in Kelvin, or actually in Kelvin scale or absolute temperature. So this is COP of heat pump for Carnot heat pump. This one is COP for Carnot refrigerator. Then, as I said, we can have these values or these equalities for the COP for refrigerator, for example. for a irreversible refrigerator, actually COP is lower than COP of a reversible refrigerator or a Carnot refrigerator. And if we have a reversible refrigerator, which we cannot actually have such a refrigerator in uh, actually, then the COP of that refrigerator should be equal to the COP of the Carnot refrigerator. And it is not possible to have a refrigerator with a COP higher than the COP of Carnot refrigerator. And as I said earlier, COP of both of the refrigerators and heat pumps can decreases as TL decreases. This is according to these two equations. So the COP of both refrigerators and heat pumps decreases as TL decreases. As I said earlier, we need to increase the TL or the temperature of the lower the reservoir with low temperature to increase the COP or coefficient of performance for that refrigerator or that heat pump. And this is due to we need to more work to absorb the heat from lower temperature media and to transfer it to the uh, higher temperature media. Then we will see some examples to see how we can calculate the efficiency or coefficient of performance for this refrigerator or heat pump. Here in this example, we have a Carnot refrigerator, and which it means it is working in a Carnot refrigeration cycle actually. Then we will see how we can determine the thermal efficiency for that and also other properties for these refrigerators. We have a Carnot refrigeration cycle, which this cycle, the cycle for that is executed in a closed system in the saturated liquid vapor mixture region or this region using 0.8 kilogram of refrigerant 134A as the working fluid. So the working fluid is this refrigerant and the mass of that is 0.8 kilogram. The maximum and minimum temperature in the cycle are 20 and negative 8 degrees Celsius. This is TH, this is TL. It is known that the refrigerant is saturated liquid at the end of the heat rejection process. And the net work input to the cycle is 15 kilojoule or W net actually. This is W net in for this refrigerant. Determine the fraction of the mass of the refrigerant that vaporized during the heat addition process. And also we need to determine the pressure at the end of the heat rejection process. First of all, let's see how we can draw this TV diagram for this cycle. As you may know, in a Carnot cycle, we have two isothermal and two adiabatic process. And the direction of the cycle, as well as I discussed earlier, is in this direction for a Carnot refrigeration cycle. Initially, it will absorb temperature. Its initial temperature is negative 8 degrees Celsius. Then the first process is a isothermal process, 1 to 2. Its temperature is negative 8 degrees Celsius, and during this process, the thermal energy is absorbed from the uh, working fluid actually. Then process 2 to 3 is the isothermal process, uh, which during that we don't have any heat transfer. with the surrounded by this and system, which is a line like this in the TV diagram, and process from state 3 to state 4 is heat rejection process. Actually, again, it is a constant temperature or uh, mm, isothermal process. Actually, so this is isothermal process, this is isothermal process, and these two are adiabatic processes. This is the and as it is mentioned, the process is like this. It is in a closed system in a saturated vapor mixture region. So this means this region. This green, almost the orange line or red line actually is the line to separate the saturated and the other region for the of the state for or phase for the substance, which we have seen in chapter 3 for water, but it is same for other type of substances as I discussed earlier. So we have heat absorption here and heat rejection uh, in this process. Now let's see how we can find this fraction of the mass and also how we can find the pressure at the end of the heat rejection process. First of all, by this equation, we can calculate the coefficient of performance for this refrigerator. It is a Carnot refrigerator, so we can use TH and TL. We have TH and TL in terms of Celsius. We need to convert it to the absolute temperature or Kelvin. Then we can calculate the COP for this refrigerator, which is 9.464. And the amount of the uh, energy which is required to run this refrigerator actually can be determined by this. Actually, this equation is like this. COP or coefficient of performance for a refrigerator, as you know, is the desired output to the input or it is like this. The desired output to the provided input. The provided input, as you know, for a refrigerator is W in, and the desired output is QL, which is the amount of the energy which we are interested to capture or absorb from the lower temperature media. So if we restructure this equation, we can find this QL. We have COP for this refrigerator, and W in also was mentioned. If you remember, it was mentioned that W in is 15 kg. So we have W in, we have COP for this refrigerator. Then QL will be 142 kilojoule for this Carnot cycle. Then, as it is requested, we are interested to find the fraction of the mass of refrigerant that vaporized during the heat addition. In other words, how much of this refrigerant actually is evaporated due to this QL absorption actually. So we first of all we need to calculate this QL, the amount of energy which is absorbed, which is 142 kilojoule, as I said, and then we need to how much energy is required for evaporation of the evaporation of this refrigerant. The required energy for evaporation or the phase change of this refrigerated is enthalpy of that refrigerated in that temperature. or HFG. We need first of all find this enthalpy of phase change for this refrigerant. So our refrigerator here is 134A. This is the table which we have properties, thermodynamic properties for this refrigerant, and HFG or enthalpy of phase change for this refrigerant at -8 degrees Celsius. Why -8 degrees Celsius? Because QL, the refrigerator temperature here, which this QL is captured or absorbed, the temperature of the refrigerant is -8 degrees Celsius. So HFG for -8 degrees Celsius. -8 degrees Celsius. Then HFG in the table is this row. Simply we can find it, which is 204.59 kilojoule per kilogram. So we have HFG. This amount of HFG means to evaporate 1 kilogram of this refrigerant, we need to have 204.59 kilojoule energy. So what the amount of energy which we have here is 142 kilojoule of energy. So this amount of energy can evaporate how much of the refrigerant? Simply we can divide the energy which we have to the enthalpy of phase change for this refrigerant. The energy which we have is 142 kilojoule, or QL is 142 kilojoule. The required energy for each kilogram evaporation is 204.59 kilojoule per kilogram. If we do this, if we solve this division, this QL is enough to evaporate just 0.694 kilogram of the refrigerant. This is the answer for the how much of the mass is evaporated. But what we are going to find is mass fraction. It was mentioned that the mass of the refrigerant in this cycle is 0.8 kilogram. Then simply mass of the evaporated refrigerant divided by the total mass of refrigerant is this fraction. So about 86.8% of the refrigerant is evaporated due to that QL absorption by the refrigerator. And to find the pressure at the end of this heat rejection process, simply because after this heat rejection process, or after the heat rejection process is here, and as it is mentioned, the temperature for uh, after this heat rejection will be 20 degrees Celsius. So the temperature of the refrigerant at the end of this heat rejection process will be 20 degrees Celsius. And as it is mentioned, it is in the whole process in the saturated mixture region. So the temperature and pressure of uh, the pressure of the refrigerant here should be the saturated uh, pressure for the refrigerant at the given temperature for the refrigerant. The temperature here is 20 degrees Celsius, so the pressure at stage 4 will be, or at the end of the heat rejection process, is saturated pressure at 20 degrees Celsius, which is from the table we can find it, which is 572. If we go to the table, this is the temperature which we have, and this is the saturated pressure for this temperature, which is 572 point approximately 1 kilopascal. This is the saturated pressure at this temperature, and also the pressure at the stage 4. The other example is for heating a house by a Carnot heat pump. In this example, we have a heat pump which is going to be used to heat a house during the winter. The house is going to maintain, or the temperature of house is going to maintain at 21 degrees Celsius at all times. So we can say that we have a steady condition. The house is estimated to be losing heat or lossing heat at a rate of 135,000 kilojoule per hour, or Q. This is heat loss from the house. When the outside temperature is negative 5 degrees Celsius, this is TL, this is QH. Determine the minimum power required to drive these heat pump. First of all, let me analyze the question. This is a schematic of what we have for a heat pump. The cold outside air temperature is negative 5 degrees Celsius. The temperature of the house is going to maintain at 21 degrees Celsius. This is TH, this is TL. The heat loss from the house is 135,000 kilojoule per hour, or Q dot H is this amount. To maintain the temperature of this house constantly in this temperature, we need to provide the amount of energy which is actually is lasting from the house, which is it lasts from the house. So Q dot H need to be equal to 135,000 kilojoule per hour. So we have Q dot H as. Then what we are interested to find is W dot net in. First of all, you need to notice that what we have here is a Carnot heat pump. And an interesting characteristic of a Carnot heat pump is we can calculate the coefficient of performance for a Carnot heat pump by this equation. We need only to have the temperature of the two reservoirs actually, which we have here, temperature of the outside and temperature of the inside the house. TL the outside, TH the inside the house. But we need to notice that the temperature here is the absolute temperature. Temperature which we have is Celsius. We need to add 273 to that to convert to Kelvin, also of the temperatures. Then this coefficient of performance for this heat pump will be 11.3. So simply after we calculate the COP, we can use the other equation which we have to find COP. COP for any type of the refrigerator or heat pump is desired output provided input. What we have here, desired output is Q dot H, provided input is W net in. If we restructure this equation, we can write W dot net in is equal to Q dot H divided by COP of this heat pump. We have calculated COP, and we need to also put here Q dot H. Q dot H, which we have, is in terms of kilojoule per hour. If we want to change it to watt or kilowatt, we can just convert like this. If we divide this kilojoule per hour to 3600, it will be converted to kilowatt. So if we simply write these values for Q dot H and COP, or coefficient of performance for this heat pump, we can calculate the required power input for this heat pump, which is 3.32 kilowatt power is required power input for this heat pump. By this example, we reach end of this chapter actually, which was about the second law. I have started to talk about the second law. Then I introduced some basic definition about thermal energy reservoirs. I introduced you heat engine. I introduced thermal efficiency. We had different statements for the second law. I introduced you the COP. And discussed about the perpetual motion machines, and we found that it is not possible to have such machines. I introduced you the reversible cycle or processes, and we learned what are the irreversibilities and what are the reasons for to have an irreversible process actually. Then I introduced you the Carnot cycle as the the cycle which has the most possible efficiency, or COP. And also I introduced you the Carnot principle, which are derived from the Carnot cycle, and those statements for the second law of thermodynamics. I introduced you the absolute temperature and also the Carnot heat engine, Carnot refrigerator, and also the heat pump. All of the information which you learn in this chapter are useful to see, especially the efficiency of different type of the cyclic device, which usually in engineering, our main purpose is to increase the efficiency of these devices. Thank you very much for watching this video lecture. For next chapter, we'll discuss about